Okay, good morning, everyone. So today we are going to be talking about the hyperfine structure of the hydrogen atom. And whenever you hear hyperfine structure, you should be thinking about the effect of the nucleus on the atomic state. In the case of hydrogen, that's basically the magnetic moment of the proton. Okay, and so last time we wrote down one piece of the Hamiltonian, which is the spin orbit for the proton interacting with the orbital angular momentum of the electron. And that turned out to be E over twice the mass of the electron, speed of light, 1 over distance cubed. That's the distance operator that tells you where the electron is. And then there's the magnetic moment operator of the proton, which is proportional to its spin, dotted into L. So that's for the electron. We're still treating the proton as if it's stationary. Okay, and then this is E squared G proton, which turns out to be about 5.6, divided by 4 mass of the electron, mass of the proton, speed of light squared. And so all I'm doing here is I'm replacing the magnetic moment of the proton by the appropriate factors times the spin of the proton. So I equals proton spin. Okay, now, so that's one effect of the proton having spin. But if you open up your favorite book on classical electromagnetism and you read about what happens when you have two magnetic dipoles that can interact, you will discover that there are extra terms for the energy, which look like the following. So there's a dipole-dipole interaction, which looks like, again, 1 over the distance between the dipoles cubed. And then it's the product of the dipole moments, the dot product. So that's for the electron and the proton, minus this weird combination 3. You dot each one of them into the radial coordinate between them, and then you divide by r squared, which has to be there by dimensional analysis. And then there's also a contact interaction. Sometimes people lump together the contact interaction with the dipole-dipole because they look kind of similar. It's again the dot product of the two magnetic moments, and it's multiplied by 8 pi over 3 times a 3-dimensional delta function of the radial of the displacement vector. Okay, so we can put all these together into one formula because they all have similar dependence on the distance between the electron and the proton. Okay, and that's what we're going to be calling our hyperfine Hamiltonian. Okay, and it's charge on the electron over twice the mass of the electron times the speed of light. And then there's the magnetic dipole moment of the proton dotted into a bunch of stuff. 1 over r cubed s minus L. So I've combined part of the dipole-dipole with the spin orbit contribution. And then there's minus 3 over r to the 5th power r dot s times r. So r dot s makes it a scalar, and then the r makes it a vector again. This whole thing in square brackets that I'm writing down is a vector because it's going to be dotted into mu. And so what goes here is a 3-dimensional delta function of r times the spin of the electron. Okay, and then I can write what the magnetic moment of the proton is. It's got the factor of G sub p in it. So here's our Hamiltonian. Okay, and there's an L minus S dotted into I plus 3 over R to the 5th, R dot S, R dot I, plus 8 pi over 3, three-dimensional delta function of R times S dot I. I is the spin of the proton operator, which in the notes I think I called S sub p. Okay, so now we're going to be calculating that as our W perturbation by doing perturbation theory. Again, it's going to turn out to be degenerate perturbation theory because of the high degree of degeneracy of the hydrogen atom. But before we do that, we'll notice that this is going to be very small. And it's very small for a couple of reasons. One is we've got the speed of light squared in the denominator, just like for the fine structure. But the other difference is, unlike the fine structure, we've got an extra factor of the mass of the proton in the denominator rather than the mass of the electron. So that makes it much smaller than the fine structure. And just a very rough order of magnitude estimate of how much smaller is the mass of the proton in the denominator rather than the mass of the electron, and that's a factor of about 1,836. So this should be about 3 orders of magnitude smaller than the fine structure. All right, so we're going to treat this hyperfine Hamiltonian as a perturbation. At first sight, it looks like it's very complicated and it's going to be a mess, but what we're going to find out is it actually simplifies a lot. Okay, and we're going to be using the states labeled by principal quantum number, orbital angular momentum quantum number, the spin quantum number, which is always 1/2, the total angular momentum, not including the proton, J, and then the Z component of that. So J is not including the proton yet, the proton spin. And we'll see where the proton spin comes in a minute. Okay, so those are eigenstates of our original Hamiltonian for the hydrogen atom that didn't include any of these spin effects, plus the fine part. That's our unperturbed Hamiltonian now. It used to be that H0 was our unperturbed, but then we solved that and we got, now this is our unperturbed. Okay, and now we're going to add new labels for the total proton spin and its Z component. Those are for proton spin. Okay, now I is fixed to be 1/2, but M sub I can be plus or minus 1/2. Okay, and so what we know that what we need to do is we're going to be doing degenerate perturbation theory. And so we want the expectation values of the hyperfine Hamiltonian, but we want to do it in a basis where it's diagonal. So we want to find a basis in which the hyperfine Hamiltonian is diagonal. Okay, so as a tool for doing that, we're going to be using something that I'm not going to prove, although I'll try to make it plausible. And that's the Lande formula. Okay, so by way of introduction for the Lande formula, suppose I have an angular momentum operator. This is sort of a generic angular momentum operator, so I'm going to call it J. And in the problem we're doing, it's actually going to turn out to be J. Okay, so an angular momentum operator, one thing it does, if we remember from last semester, is it generates rotations. Okay, and so we can take any operator that looks like it might be a vector operator. So I'm going to call it generically A. So it's something that's got three components, but it's not just anything that has three components. The three components have to transform as a vector. So when I say it's a vector operator, it transforms under rotations. Just like the position vector R. Right? So that means if I do a rotation that sends the x coordinate of R into the y coordinate, then the x component of A has to be transformed into the same way as the y component of A for that particular rotation. Okay, so that's the setup. I've got some angular momentum operator, and I've got a vector operator that transforms under it. And so here's the Lande formula. It says, if I compute the following matrix element, so I'm computing matrix elements of a vector operator, which means it's going to be a vector. The result will be a vector. And I'm doing it between states that have the same J angular momentum, but different or possibly different Z components. That's why MJ and MJ prime here. And so the claim is, so first of all, that's three numbers that we're computing in one, because we're computing a vector operator. And the claim is it's a scalar quantity, namely this, the expectation value of A dotted into J. Okay, and notice here, we put the same M sub J, okay, multiplied by the matrix element of the J operator. And here, so the left-hand side depends on M sub J, depends on M sub J and prime. And so the right-hand side must also, and that's where the dependence on M sub J prime comes in. And then to make everything work out, we have to divide this by h bar squared J times J plus 1. Okay, so I'm not going to prove this formula. You're supposed to just believe it. But one thing we could do is we can check and say what happens if A happens to equal J. So we can do that because J is itself a vector operator. J transforms under rotations generated by J. And so if we do that, then this whole first factor here in the numerator, I've got J squared, and J squared acting on this state gives me the same thing as the denominator. So that means the whole first factor is just 1, and I get that this with A equals J equals that, where it's the same thing, where it's the same thing with J, and so everything works. Okay, so the first factor in that case is just 1. But the point of this is that for any other operator J, if we want to compute it, we know what these matrix elements are. because we know that from the theory of angular momentum. And so all we have to do is compute this one number in front. Notice this is a scalar operator because we're taking the dot product, so there's only one number to compute there. And then we'll have the whole thing. Okay, so this is a special case of the Wigner-Eckart theorem. Which we will also not prove. Okay, but this is actually the most useful version of the Wigner-Eckart theorem. The Wigner-Eckart theorem actually deals with more complicated things like tensor operators. And if you're dealing with things like quadrupole moments, then you need the full power of the Wigner-Eckart theorem. But if you're just dealing with vector operators like we're going to be doing, then this simpler version that I've written down here, the Lande formula, is what we need. Okay, so that's our tool. And now we ask, what are we going to apply this to? We're going to apply it, if we go back and look at our formula up here, we're going to be applying that to evaluate this whole part right here. We're going to leave the delta function part for later. And so we notice that this is all a bunch of stuff dotted into I, and the bunch of stuff is going to be our operator A. Okay, so we're going to line here. We're going to be applying this with, first of all, our angular momentum operator is going to be L plus S. So again, it's the total angular momentum, not counting the proton spin part. And our vector operator is going to be A equals 1 over r cubed L minus S plus 3 over r to the 5th S dot r times r. And the reason for that is that's the matrix element that we need to compute. So you could say, well, wait a minute, you're not including the proton spin, so how can you use this? And the point is, our operator A here also doesn't include the proton spin. And so when you're talking about whether it transforms as a vector when you're generating rotations, it does, because the fact that we're leaving the proton spin out, which we would normally include in a true total angular momentum, just doesn't matter, because nothing in A itself involves the proton spin. Okay, so if we look at our Lande formula, we need the dot products of this A with J. And so what we need are the following matrix elements: L minus S dotted into J, and there's a 1 over r cubed that goes with that, and 1 over r to the 5th r dot S times r dot J. Okay, we need those matrix elements because we're going to be plugging them into here. And then once we do that and multiply by this quantity, then we'll get the whole thing that we need. Okay, so let's concentrate on doing those two matrix elements. So I'll call that 1 and this one 2. So first, for 1, we can use the fact that L minus S dotted into J is otherwise known as L minus S dotted into L plus S, which is otherwise known as L squared minus S squared. And that's nice because we know that if we're working in eigenstates of L, this is just h bar squared times L plus 1 minus S times S plus 1, but that's fixed to be 3/4. Okay, and so sandwiched in any matrix element that's an eigenstate where we're doing eigenstates of L, that will be a number. We can just replace that by a number. Okay, and then second, for the part 2, we can use the fact that R dot J is equal to R dot L plus S, which is R dotted into R cross P plus R dot S. And now the thing about R dotted into R cross P is regardless of whether it's an operator or a real vector, you take anything dotted into a cross product of the same thing and you get 0. So this is 0, and the only part that matters is the spin. So when we're computing that second expectation value, we've got R dot S times R dot J is just the same thing as R dot S, R dot S. And now we can use the representation of the spin in terms of Pauli matrices. This is going to be h bar squared over 4 R dot Pauli matrix times R dot Pauli matrix.
Professor?
Yes?
Is there a parenthesis missing in that previous line?
Probably. Oh, here? Yeah. Actually, I don't need that parentheses there. There's an extra one.
Thank you.
Good. Okay. So we've got R dot sigma, R dot sigma. Sigmas are the Pauli matrices. And if you remember in the dim past of last semester, when we were talking about the Pauli matrices, we remembered that if you've got the same vector dotted into a Pauli matrix multiplied by itself, you just get the vector squared. And so this is h bar squared over 4 R squared. So I should say we're only doing here the expectation value of the angular momentum parts of these operators. We're later going to be doing the R parts. So we're going to use the radial coordinate later. Okay, so anyway, so we had these two things. And we worked out this one, which had a -3/4 in it. And this thing had a 1/4 in it with an R squared, but there was a 1 over R to the 5th. So it turns out the R parts are the same. And this one also had a multiple of 3. And so this ends up just neatly canceling that. And so the answer is much simpler than we had any right to expect. Namely, the matrix or the expectation value of A dot J in a state with angular momentum J is h bar squared L times L plus 1 over R cubed. So naively, you might have thought, or I might have thought, that it would actually depend on J, but it doesn't. It depends only on the particular combination L. That has to do with the fact that the spin is 1/2. Okay, so now if we're going to apply this in any matrix elements, so I shouldn't say matrix elements, I should say more specifically expectation values. Of course, an expectation value is a special case of a matrix element. So in expectation values of states with labels N, L, S, and J, the hyperfine Hamiltonian boils down to there's a prefactor, E squared G proton, which is about 5.6, twice the mass of the electron, mass of the proton, speed of light squared. That's going to be a very small number, times L plus 1. That's from here. Divided by J times J plus 1. That factor comes from way back up here in the Lande formula. And then there's this factor, but that's going to get dotted into the I operator. So what we're going to be left with here is J dotted into I times 1 over R cubed. And then there's the delta function part that we've been not talking about for the last few minutes, which looks like this. So there's a J dot I part and there's a spin dot I part. Okay, and we need to now evaluate the expectation value of that, now taking into account the proton spin and the radial coordinates. So before we do that, we notice a nice fact about this, which is the first term only contributes if L is not 0. And that's just because it's got an L in the numerator. So only contributes if L is not 0. And because of this three-dimensional delta function, the second term only contributes if L equals 0. And the reason for that is because the wave function at the origin for the hydrogen atom, as we proved, is 0 for L not equal to 0. Right? So you imagine this electron spinning around the proton. If the angular momentum is non-zero, then there's the centrifugal force that's pushing the electron out. And so it has no overlap with the origin unless L equals 0. So that means we can divide and conquer. For any given state, we only have to consider one of these contributions and ignore the other one. And so we can compute that way. Okay, so let's do the L equals 0 term first, or that case first.
I'm sorry, Professor.
Mm-hmm.
Could you explain one more time why that the psi squared was 0?
So it's 0 unless L is 0. And I was giving a heuristic reason, a sort of hand-waving version of it is that if L is non-zero, then the centrifugal force is pushing the electron away from the origin and it has 0 overlap with the origin. The alternative way, the more rigorous way, is to just look at the wave functions of the hydrogen atom and notice that there's a factor of R to the L. So these wave functions actually behave like R to the Lth power. And so if L is non-zero, that will vanish when R equals 0. On the other hand, when L equals 0, then that is just 1. And so it approaches a constant as R goes to 0. So this is not unrelated to your homework this week. All right, so let's look at the L equals 0 case. That means we get to ignore the first term. Okay, and this includes the n equals 1 ground state, because the n equals 1 ground state only has L equals 0. It doesn't have any other L's. But it also applies to other states when you're talking about the L equals 0 part. Okay, so if little l equals 0, that means acting on those states, big L, the operator is 0. And so when we look at S dot I, we might as well call that J dot I. It's the same thing. And now we're going to use the usual trick when we see two angular momenta dotted together. We realize that's probably going to involve 1/2 the sum of the angular momentum squared, which I'm going to call F. We need lots of symbols for different angular momenta. So this is going to be F squared minus J squared minus I squared, where F is an angular momentum that we get by combining J plus I. So that's the real true total angular momentum. It's orbital plus spin of the electron plus spin of the proton. Okay. So it's an angular momentum. That means what are its eigenvalues? F squared has eigenvalues that are h bar squared times F plus 1, as usual. And F is going to be an integer. So the reason F is going to be an integer is what are we doing? We're combining orbital, which is an integer, plus 1/2 for the electron spin, plus another 1/2 for the proton spin. So we're combining two 1/2s, which gives a 0 or 1, and then L, which is always an integer. Okay, and F sub z, the z component of that angular momentum has eigenvalues h bar times m sub f. Okay, and so m sub f takes on, as usual, two F plus 1 values. So before we even go any further, we should say that just in general, not just for the L equals 0 case, but for any case, that's what we're really doing here, because I was saying L equals 0, but this will apply to L equals 17 for that matter. The total angular momentum is the thing that generates rotations of the entire system. And so there's no way that anything can depend on m sub f as far as energy, because the whole Hamiltonian has to be invariant under rotations. That's just saying there's no special direction in the universe, right? And so this has to be an ultimate degeneracy that we're never going to get rid of. The only way to get rid of this is to actually introduce some new special direction. We could do that by putting our atom in a magnetic field or an electric field or something like that. But we're not doing that. We're just thinking about the atom sitting in ordinary space. Okay, so what does that mean? That means we should use an orthobasis that's diagonal. And so our orthobasis will have the following labels. There's the principal quantum number. There's the orbital angular momentum. There's the spin, which is really fixed to be 1/2. There's the spin of the proton, which is also fixed to be 1/2. There's F, which is going to be 0 or 1 in this L equals 0 case, but in general, it's an integer. And then finally, there's the M sub F, which is a real degeneracy label. Okay, and in that basis, our hyperfine Hamiltonian will be diagonal. And in fact, let's compute its expectation value. I'm having trouble with my pen here. Okay, there's our prefactor. And then there's 8 pi over 3 times the expectation value of the delta function. Okay, and that's the wave function delta function, so it doesn't depend on any of these spins. That's why I just wrote N and L here. It only depends on the orbital parts. And then there's h bar squared over 2. I'm going to be plugging in this stuff times f plus 1 minus s times s plus 1 minus I times I plus 1. This is 3/4, and this is 3/4. And f is either 0 or 1. So this first term is 0 for f equals 0. And the other possibility is it's 2 for f equals 1. Okay, and then there's this part, the radial part, which is just a calculation. Again, not unrelated to your homework. And so that turns out to be 1 over pi n cubed times the Bohr radius cubed. Okay, and so we're finally ready to put all of this together. The change in the energy due to the hyperfine interaction. This is only for the L equals 0 states, is 4e squared h bar squared g proton. So this is just this prefactor that we've worked out. Oops. M proton c squared, Bohr radius cubed. The n dependence is it's 1 over n cubed. That's coming from the wave function at the origin squared. Let's see if I got all my factors straight here. And then, oops, and then we have to evaluate this mess. And when we do that, we get either 1/4 for f equals 1, or we get minus 3/4 for f equals 0. Okay, so that's the hyperfine correction. It depends on the total angular momentum f. And we can rewrite this prefactor here as 8/3 mass of the electron over the mass of the proton, gyromagnetic moment of the proton, and then there's the same stuff that we get for the fine structure. So alpha squared times a Rydberg. Okay, so this was the fine structure energy. And now it's being multiplied by this 1 over 2000 factor. And it happens to get multiplied by 5.6, and then this is 2 2/3. So it's not quite as small as one might naively have guessed, because it's getting multiplied by an extra order of magnitude, more than an order of magnitude from these numerical factors. Okay, so numerically, that prefactor, it turns out, is 5.878 times 10 to the minus 6 electron volts. So it's about a micro electron volt. And if all of this seems familiar, it's because we've already talked about the hyperfine structure. But before, when we talked about it, I just gave you a dot product of 2 angular momenta and said, figure out its eigenvalues. And so the difference is that now the way we've done it is we are actually started off with a real Hamiltonian, and we computed this prefactor instead of just assuming it as a number. So that's the main difference, but otherwise it's the same thing that we did before when we talked about the hyperfine structure. The applied to the n equals 1 state, it tells us that the 1s 1/2 ground state splits. It's splitting because of the spin of the proton. So due to proton spin. And so classically, you can think of this as just, or semi-classically, you can just think of this as due to the proton being able to flip up and down, for example, when it's applied to a magnetic field. And so when the F equals 1 state, which notice has a higher energy because this is plus a quarter and this is getting driven down, minus 3/4. When that state decays to the F equals 0 state, there's a photon that gets emitted with the difference in energy. E gamma, which is this prefactor, 5.878 times 10 to the minus 6 electron volts that we computed. Okay, and so from that, that is equal to h times nu, so we get the frequency. The frequency nu is 1.42 something times 10 to the 4 hertz. Actually 10 to the 9 hertz. Okay, and that's, well, wavelength is about 21 centimeters. That's because it's the speed of light divided by nu. And so there's this transition from the F equals 1 state, which by the way is a triplet. It's a triplet because the degeneracy that we can't get rid of is in M sub F, 1, 0, and minus 1. And the lower state is the singlet. It's a singlet because in that case, M sub F is just 0. And we emit a photon in going from one state to the other, or you can absorb a photon and see, so for example, you might see a deficit of photons with a certain energy. And it turns out, and we'll discuss the reasons for this later in the course, it turns out that this is a very strongly suppressed decay. In other words, this decay doesn't like to occur readily. We'll discover the reasons for that when we talk about interactions with electromagnetic field. But this is the 21 centimeter line used in radio astronomy. There you benefit from the fact that even though this decay doesn't happen very often, there's a very large amount of hydrogen in the universe and space is very big. And so you get to see this anyway. Okay, so all of this was for the case where L equals 0. And so now let's treat the case where L is not 0.
I'm sorry, Professor?
Yeah.
Was that a 10 to the 9th power in the hertz?
Yes.
Okay, thank you.
Okay, so now for the L not equal 0 case, which means for that for sure n is greater than or equal to 2. And again, we're going to use the same ortho basis because this is the ortho basis in which the hyperfine Hamiltonian is diagonal. So N, L, S, J, F, and our degeneracy label M sub F. And now J dot I is the thing that appeared, which is 1/2 F squared minus J squared minus I squared again, which is H bar squared over 2. F times F plus 1 minus J times J plus 1 minus 3/4. That's for I because I is fixed to be 1/2. And so now we're evaluating the expectation value of the hyperfine Hamiltonian to get the first order correction to the energy. And so we've got here E squared G proton, the same sort of prefactor. But now instead of the expectation value of the delta function, we have the expectation value of 1 over r cubed. And then there's L times L plus 1 over J times J plus 1. And then there's the factor that we just found in the above line. Okay, and when we did the fine structure, we worked out 1 over r cubed. You're also doing it for homework. So we've really got that covered. This is 1 over Bohr radius cubed, n cubed, L times L plus 1 times L plus 1/2. Okay, and a nice thing that's going to happen is that the L times L plus 1/2 here are going to cancel out. Okay, and the other thing is that we should keep in mind is what can F be in terms of J? F can be J plus or minus 1/2, because to get F, we're taking the J quantum number and we're adding a spin 1/2 to it. So it either raises it by 1/2 or lowers it by 1/2. Okay, and so we can plug that in and we get the hyperfine correction to the energy is, I'm going to write my alpha squared here. So this alpha squared is coming about from a combination of the E squared and this Bohr radius. So there's an alpha squared, there's a E squared over 2a0. That's the Rydberg that sets the overall energy scale. Mass of the electron over the mass of the proton. There's my GP factor. And then there's a 1 over n cubed, which is coming about from my expectation value of the radial coordinate, 1 over the radial coordinate cubed. And then all the other stuff here, all of that stuff, not including the h bar. Actually, that should have been an h bar squared. Okay, all of that other stuff arranges itself into plus or minus 1 over 2L plus 1 times F plus 1/2. Okay, and this is for F equals J plus or minus 1/2. Okay, so there's our formula. And then if you stare at this for a while, you realize that actually this formula even agrees with the L equals 0 formula too. So this formula works for all cases, just sort of by accident. I guess there's no such thing as accidents. But in any case, it agrees with the L equals 0 case. And so having noted that, that's the formula that works for all cases. So this is true. This is true for any L, including L equals 0. Okay, and so the lesson that we've learned is that the hyperfine Hamiltonian splits each NLSJ level. These are fine structure levels into 2. And the 2 are just whether how the proton is oriented with respect to the other components of the angular momentum. Okay, so in terms of, let me call E gamma to be just the factor that we get from the ground state from the 21 centimeter line. Okay, so it's the fine structure part times the other suppression factors. Okay, and if we do this for the n equals 2 level, this is the first excited level of the hydrogen atom. Okay, so at the fine structure level, there was a 2s1/2. Let me leave some space and put down here a 2p1/2. And then there was a 2p3/2. Okay, this means L equals 0, J equals 1/2. This is L equals 1, J equals 1/2. This is L equals 1, J equals 3/2. And so this gets split into F equals 1 and F equals 0. This gets split into F equals 1 again and F equals 0. And this gets split into F equals 2 and F equals 1. Okay, and the corrections to the energy are E gamma over 32 minus 3 over 32 E gamma. This one is E gamma over 96. This is minus E gamma over 32. This one gets a correction E gamma over 160. And this one gets a correction minus E gamma over 96. Okay, and so the total splitting here is between those two states is E gamma over 8. This is E gamma over 24. And this is E gamma over 60. Okay. So note each F squared eigenstate remains with this degeneracy that you can't get rid of 2F plus 1. The only way you can get rid of it is by introducing a special direction in the problem, like putting in a magnetic field or something like that. Okay, so we're out of time today. But next time I'll say a few more things about this hyperfine splitting. And then we'll talk about something else that turns out to be important that is much more difficult to calculate, and we'll just quote the answer, called the Lamb shift. The Lamb shift requires basically doing quantum field theory. You can't get it from doing the naive perturbation theory the way we've been doing it, at least not in an easy way. But it turns out to be numerically comparable to the hyperfine. Okay, so next time we'll talk about Lamb shift, and then we will map out the n equals 2 level completely. And then for homework, you'll get to do the same thing for the n equals 3 level, which isn't as daunting as it sounds, because we will have all the formulas, and you'll just have to plug into the relevant formulas. All right, sorry for going over time today. Are there any questions on any of this?
So Professor, what exactly is this doing? Is this like splitting? Is this like magnetic field splitting these like levels or orbitals in an atom? What exactly is happening here?
So what's happening is the magnetic interaction of the proton is splitting apart the states that would otherwise not be split. And by otherwise, I mean, if we ignore the proton's magnetic moment, there would be still this degeneracy. And the proton spin is interacting with the electron to split them apart by a very tiny amount.
It's splitting up. I'm sorry, say again one more time, please. What exactly is it splitting up again?
It's splitting up, for example, the 2s1/2 level is being split into 2 different levels. The 2p1/2 is being split into 2, and the 2p3/2 is being split into 2.
So what does it mean it's being split into 2? Are those like when we had those shapes like of the electron cloud in a field? What do you call it?
No, it has nothing to do with the wave function directly. It's just the energy level, right? There was an energy level that had some degeneracy, and it's being split into 2 different energy levels. So this is a 2p1/2 energy level that had some degeneracy, and now it's being split into 2 levels with slightly different energy. These are the corrections to the energy that I've written here, right? And so these are very small numbers, but before including the hyperfine, this was 1 level with some degeneracy to it, and now it's been split into different energies.
So those electron clouds that were like what they call those pi, and they had different names for those. Like so this has nothing to do with those electron clouds that the electrons that um, when like those clouds, those shapes that they show in chemistry that when they like surround the proton, what is it like?
Right, we're not calculating anything to do with the wave functions here. We're just calculating the corrections to the energy, not the wave function.
So this doesn't do anything to the wave function itself. Is that what you're
So
saying?
that's another thing. The perturbations do affect the wave function by a very, very small amount. That's probably too small to worry about for anything. But the energies can be measured directly because you can look at transitions between different energy states. So that's why you can measure it. We're just not calculating or worrying about the corrections to the wave functions. We could, but it would be very complicated and it wouldn't actually teach us anything that we could measure very easily. Whereas the energy levels can be measured very precisely. Okay.
Thank you. I also had a question on the homework.
All right. Let me stop the recording here.